morning, everyone. Welcome back. Today we have electron microscope physics and optics. As our microscopes have become fancier and more expensive, they've literally turned into big black boxes. So I'm very excited that Chris Russo, a postdoc in Laurie's lab, he's actually a physicist, he was at Harvard before, and I'm very excited he will be telling us all about what goes on inside the black box. Thanks, yours.
Okay, so I think Tony on Monday introduced this thing as a big black box, and I think he called it a TARDIS. So I like the metaphor actually, and as we go through the talk, I think you'll see more and more why I like it. But I think what he meant by it was that indeed it is, for most people, this thing is a big black box. You stick a sample in one side, and a bunch of data comes out the other side, and then that data goes into some more black boxes hidden away somewhere, and then you get some sort of threatening emails from Jake about doing bad things to the cluster, and then all of a sudden you have your structure. So I'm hoping we can actually go into this box a little bit more, and I can convince you that you can understand how it works, and the deeper you go into it, the more interesting it gets, at least for me. But not only that, even if you don't understand all the details, you can know enough that you will be a much better microscopist and do a much better job of getting to your goal, which is a new structure. So if you take the box off, this is what it looks like. I'm not going to lie, it's a bit complicated. There's a lot of pieces to it. But ultimately, this thing is really just a microscope. And it's a microscope in the same way that this is a microscope, in the same way that Leeuwenhoek's was a microscope. And so I'm just going to remind you of the basic pieces of any microscope. Somehow you have some source of light, in this, or photons, if we want to be fancy about it. And those photons have to get to the sample and somehow interact with it, and then we use a lens to make an image of that interaction. And that image, which ends up somewhere over here, we somehow have to detect. And with most light microscopes, it goes into an eye, or even more commonly a camera nowadays. And an electron microscope is really nothing different. So if we look at this in terms of a lens diagram, the main things to take note of is that you have some object that you're trying to image, and you have an object lens, or what we call an objective lens. And that's really the business part of the whole microscope. This is the thing that actually forms an image of the object. And the image, we call it the real image if it's in the opposite focal plane. And if we reproject this onto some detector, we see a virtual image that can be magnified. Right? So this is the virtual image, this is the real image, this is the object, this is the lens. And this would be what we would call a projector lens in an electron microscope. Okay, so if all microscopes are built this way, so how is an electron microscope built? We'll get to that in a minute, but first we have to say, why do we want to use electrons? So I think this slide should motivate you. It's a bit of a historical slide. So the progress in optical microscopes started here in the 1800s and quite rapidly progressed as lens design and the ability to grind more and more accurate and better lenses. But eventually it petered out because of the diffraction limit of light. And now super resolution techniques and really fancy and clever people can push this up to maybe about here. This is say 10 nanometers. So you can easily see why an electron microscope is interesting, because it can go orders of magnitude higher in resolution because it's not limited by the wavelength of the particle you're using. And in fact, for most of the work we do, it's never been limited by the wavelength. And I think Shores mentioned that yesterday. This is a picture of the first one, by the way. You can see it. It's in a museum in Munich. Well, anyway, let's talk about what a very basic electron image is. So the way we make an image with electrons is using scattering, right? So the beam of electrons hits the atoms in the specimen, and eventually they interact with it and are scattered. Most of them actually aren't scattered, but the ones that are scattered can be removed by using apertures, or they can be focused into different planes and used to construct an image. So really, electron microscopes are really all about scattering. And this is in contrast to some forms of light microscopy where we talk mostly about absorption and re-emission. Right? So in electron microscopes, the fundamental process is electron scattering with the sample. Okay. So if you take a high energy electron and you shoot it into a sample, what happens? Well, a whole lot of things happen. And in fact, there's actually a microscope for every single one of these interactions that go on. But the ones we're really interested in are these elastically scattered electrons, because these are the ones that act very nicely like waves, and they get focused by optics, and we can use them to create images. And we also take advantage of the fact that there's an unscattered beam there as well, and we'll talk about that in a minute. Okay, a little bit more about electrons. And we're going to start putting equations up. Don't get scared. It's going to be fine. But there's a few properties of electrons that are quite important, especially electrons in the microscope. And you can actually work out the details of these things using very simple back-of-the-envelope calculations. And so I'm going to give you an example of this. There's an interesting experiment to think about, is that how many electrons are in an electron microscope column at any one time. So if I tell you that an electron microscope has about 0.1 nanoamps of current, that's a typical beam that you would make. So that's 10 to the minus 10 coulombs per second of electrons going through the column at a time. And there's 10 to the 18 electrons in a coulomb. So that's about 10 to the 8 electrons per second going through the column. Now, what the point of this plot that I'm showing you here is that a 300 kilovolt electron is moving enormously fast. So this is the electron energy, and this is beta. So this is the fraction of the speed of light, right? So at 100 kilovolts, you're moving half the speed of light. At 200 kilovolts, you're moving 0.7 times the speed of light. So at 300 kilovolts, you're nearly 3/4 of the speed of light, right? It's actually extremely fast. And this is where I'm going to start trying to convince you that this thing is more like a TARDIS than you might imagine. Because at 3/4 of the speed of light, the electron is twice as heavy as it would normally be, right? Its mass increases. Not only that, but time slows down. So if you had a clock that was traveling along with your electron, that clock would run at almost half the speed of a normal clock, right? So it's really mysterious stuff going on here when you go to these high energies. So it's a bit crazier than you think. But anyway, we can still do a simple calculation. So I just told you that it's moving at, let's say, 2/3 the speed of light. So the speed of light is 3 times 10 to the 8 meters per second. So if we say it's 2/3, so then that's 2 times 10 to the 8 meters per second. And a typical electron microscope, like the one Shausha was standing next to, is maybe 2 meters tall. So that's 10 to the minus 8 seconds for an electron to go from the top of the column to the bottom. So it doesn't take much to realize that 10 to the 8 per second and 10 to the minus 8 seconds means that there's only one electron in that column at a time, right? So these electrons are coming through this, they come off the top, and they shoot down, hit your sample, and hit the detector before the next one is even rolling through. So this is wild. And the reason it's wild is because Shore's just spent an entire lecture explaining to you about how these are waves and how we use them, the waves of each electron interfere with each other, and we use these to make images. But how the heck can they interfere with each other when there's only one in the column at a time? And so this is really deep mysteries, and this requires quantum mechanics to understand it. And in fact, I don't think anyone really understands this, right? So this particle-wave duality and the fact that there can be non-local action between these particles is really important, and it's a fundamental physical problem. So I think, an electron microscope is an absolutely fascinating box, and the deeper you go into it, the more mysterious it becomes. Okay, enough mystery. So we did this calculation. Now, a few vocabulary words, again, that I want to remind you of just to make sure that you don't make the mistake, because it happens a lot. Voltage is a measurement of electrical potential. It's not an energy. Electron volts is an energy. So if you talk about the energy of your microscope in volts, you're making a mistake. You should talk about it in electron volts. We often do it. It's a colloquialism, but if you're going to write a paper, you should put electron volts if you talk about energy. Dose, fluence, and flux. Dose. We often talk about electron dose as the number of electrons that go through a sample in a given image or in a given period of time. But the radiation chemists and radiation physicists would argue with this. So to them, dose means the amount of energy you've deposited in a sample per unit volume. And these things have very different units. But this one you can get away with. Just be sure that you specify what you mean when you do it. Because when we say dose in an electron microscope, what we usually mean is fluence. And that's the number of particles that have transited through a unit area in a given time. And flux is the rate at which those particles, so that's how many are going through per second, and the total number that you put through a particular area is the fluence. Okay. Right. So let's talk about the problems. Electron microscopes. What are the problems with electron microscopes? Well, number one, electrons don't go through air, right? They get scattered very rapidly, and so you have to put everything in vacuum. And we have to, not only that, but you have to use pretty good vacuum. You have to use very fancy little jet engine pumps, like this one I have sitting here on the bench, which you can come take a look at afterwards. We have to use much larger ones than the real microscopes, but this is what they look like. They're quite expensive, and and it took years to develop the technology to be able to make these things. So these are the way we create vacuum. But not only that, even worse for us, your sample has to go into vacuum. And as you all know, biology doesn't happen in a vacuum. It happens in air or in water. And so you have to make your samples compatible with this. And a big part of the development that Tony talked about on Monday in electron microscopy has been actually figuring out how to get samples into this weird place that is the inside of an electron microscope. The second thing is damage. So the other thing I want you to realize is that not only are electrons moving at this speed crazy, they're also unbelievably damaging. They have enormous amounts of energy, right? So an electron microscope beam hitting a sample is just like, taking your sample and putting it into the core of a nuclear reactor, right? It's the same level of flux of particles. And then you have to realize it's just amazing that we even get any information out of this when we do it. And Lori's going to talk some more about this and how we get around this problem. The next problem, electron lenses. They're actually really bad. So we'll talk about it a little bit more in detail, but basically lambda for lambda, if you compare it to an optical microscope, an electron microscope lens is about as good as the bottom of this water glass, right? And so we have to deal with that problem as well. What else? Large, noisy images, lots of data. I don't think I needed to tell anybody that. Charging, so hitting things with an electron beam generates other charge, and that charge can actually end up lensing the beam as well. Samples must be very thin and are very fragile, and as you know, they're quite difficult to make sometimes. And then this keeps getting worse, but on the other hand, it gets better compared to other options. So, okay, so let's go inside and have a look. So what we're going to do is trace an electron from the top of this thing all the way to the bottom. And but before I do that, I have to do a brief introduction to ray diagrams, because instead of giving you lots of complex formulas and integrals, one of the simplest ways to understand optics is using these ray diagram constructions, right? And this is an example of one for an entire electron microscope. So you can take all of the complicated optics in here and boil it down to something like this and really understand a lot about what's going on. So a normal convex lens looks something like this. It has a focal point, just like if you take a magnifying glass and you focus the sun on a leaf and you start burning a hole, that's the focal point. So it takes parallel rays and focuses them to a point. So you can create this construction by drawing a line through the center of the lens to your object, and then draw a parallel line to the lens that goes through the focal point. And immediately you can see exactly what happens to an object in the image plane. And this is a very useful way to understand lenses. So, okay, that brief aside, let's talk about the source. There are really two and a half kinds of sources in an electron microscope. The vocabulary, you talk about three different kinds: field emission, shock emission, and thermionic emission. But really, there's a continuum between these three. But I'm going to explain each of them in detail. So the thermal emission sources are created by, let me back up a second. So we want a beam of electrons. So how do we get electrons out of their natural state, which is bound to atoms, and pull them into vacuum, right? So this is an energy diagram. Energy is along this axis, and this is, some x-axis, some spatial axis, right? So this is a wire, and this is the edge of the wire. So we have a bunch of electrons sitting here in this Fermi sea of the metal. And you can think of this as just like a pot full of water, where the electrons of the water are sitting in here. And the pot has a lip on the edge, and this is the energy barrier that they have to overcome in order to come out into the vacuum of space. And this energy barrier, we can get the electrons off of here in different ways. The first way we can get it off is just to heat them up. Basically, we boil the electrons, and then a certain number of them can escape over the top of the energy barrier. That's called thermal emission. Now, if we start to apply a voltage to this, so we apply a voltage along this axis, we can start to lower this barrier. This barrier, by the way, is called the work function of the material. But that's not that important. What is important is that as you apply a voltage, you lower that barrier more and more. And eventually, if you apply a high enough voltage, you lower this barrier so much and you reduce this distance so much that quantum mechanics takes over. And the electrons inside here can actually tunnel right through here and magically appear on the other side. So, and this is what's called a field emission source, right? So here you're using the electric field to actually pull the electrons right out of the metal. Now, like I said, there's a continuum between these two, because you can heat up the metal in a field emission source, or you can just heat it enough so that you get lots of them coming off the end. But either way, you end up with a beam of electrons. Okay, so let's start with the thermal emission source. It looks something like this. I'm sure all of the native German speakers are going to cringe when I try and pronounce this, but I'm going to do it anyway. So the Wienheld is this thing here. And if you want to see a real one, it's right here. You can come and have a look at it afterwards, as long as you I promised Christos that I wouldn't get any fingerprints on it, so don't get any fingerprints on it. But this is out of one of our microscopes, so the source, it's about this big. And right inside the tip of the end of that thing is a filament, and that's schematically drawn here. And that's where the electrons get boiled off of. And my laser pointer is dying, so I'm going to switch. So the electrons get boiled right off of the end of that tip. So we run a current through the end of here, we heat it up to thousands of degrees Celsius, and that's enough to boil off enough electrons that we can start pulling them off, and we form a beam of electrons. And the Wienheld is actually the first lens in this system, and the anode is down here. So this crossover point is the thing that we actually use as the source in the optical system. This is what it looks like if you zoom in. This is the filament itself. It's a little hairpin. And when you look at it on the screen in the electron microscope, it looks something like this. Right? So this is the image of the electrons coming off of that tip there. And this is in an underfocused case. This is a very poorly focused case, and this is a nice centered and focused case. So generally, when you're doing a gun alignment, the goal is to eventually get something that looks like this, where the electrons are coming off right along the optical axis and going through a nice uniform crossover. Okay. Now, field emission sources. So remember, the field emission source, you're basically applying a very high voltage to a tip. And one of the best ways to make a very high voltage is actually to make something sharp. Right? So this is the sharp tip on the end of a field emission source. You can think of it just like a lightning rod. Field strengths are concentrated on the sharpest tips. Right? So just the same way the field strength on the top of a lightning rod will attract a lightning bolt, the same thing happens here. The voltages get much higher and higher. The voltages remain constant, but the fields actually get higher and higher as you make this sharper and sharper. And so this tip is in the center of the source, and we pull the electrons off, create a crossover, and end up with a beam. Now the main things to realize with a field emission source is that basically it's like going from a light bulb in an optical microscope to a laser. It's much more coherent, it's much brighter. It has a smaller spread in energy, and all around makes imaging a lot easier. So the Polar and the Cryos have a source like this, whereas the T12s have the other source that I told you, which is right here. Okay, a quick table to compare these things. There's some interesting numbers here. and these are the temperatures. You heat these things up a lot. Actually, our field, so this is a cold FEG. We heat ours up a bit more than that. But the really interesting number is here. So the density at which you can focus that little spot at the beginning is a measure of how good this thing is. And you can see it's 10 to the 4 here, whereas it's 10 to the 10 in the FEG. And this is really a huge difference and makes a big difference in imaging. And the other thing to notice is this difference. So the vacuum you have to have around the source, the vacuum around that source is 10 to the minus 2 Pascal, whereas the vacuum in a FEG needs to be more like 10 to the minus 7 or 10 to the minus 8 Pascal. And that's why they cost $1 million. So this really tells you the difference between these sources in many different ways. Okay. So we have a beam of electrons. How are we gonna make a lens? So before I tell you how do we make a lens, I have to tell you how we move an electron. So for the students in the room, this would be the only equation I would really pay attention to. Right? There'll be plenty more equations, but this is the one you want to remember. So this is the force on an electron, or any charged particle. Actually, it's called the Lorentz force, and it's a product of both the electric field and the magnetic field times the velocity of the electron. Now here, it's proportional to the electric field, but it's times the cross with the magnetic field. So let me explain what that means. So if you had two charged plates here, you have an electron which has a negative charge, you have a positive charge here and a negative charge here. As the electron goes by, there's an electric field here and it's attracted to the positive plate. Minuses attract pluses, right? And you bend the electron's path. Similarly, for a magnetic field, here the magnetic field is pointed out of the board, right? So it's going in this direction. And as you go through, the cross product between the velocity of the electron and the magnetic field causes the electron to spin off its normal path and into this trajectory. So this is the only way you can move electrons around, and one way or another, all electron lenses use this principle. These are the two simplest and most common types of electron lenses. The top one here uses that electric field. It's called an Einzel lens. These are the charged plates. In this case, they're in a tube, so if you put your beam of electrons in one side, it gets focused on the other side. We don't use these in electron microscopes, and the reason we don't use these is because we use very high energy electrons. So in order to make these lenses, you have to have extremely high voltages, and it becomes very difficult to do this. So because electrons are so light and it's so difficult to bend them, you have to put way too high voltages. So we basically don't use these. We use these. So these are, this is just a coil of copper wires in a cylinder, and the current going through all of these wires generates a magnetic field. We wrap it in iron like this so that the magnetic field is concentrated right at the center of the lens, and this is called the pole piece. And it's here where the magnetic field pushes on those electrons and forces them to change their path. And I have actually an objective lens from an electron microscope here. This is an old one from one of our old microscopes where after it died, so afterwards you can take a look here, you can actually see the copper coils. You can see the dimensions. This is how big a real electron microscope lens is. This happens to be from the F30, or was from the F30. Obviously it doesn't work anymore. But you just, when you're turning that knob on the electron microscope, you're really changing the amount of current that goes through one of these coils. And that's what's moving those electrons around. So, okay, so that's a lens. This is what it looks like in the Polara. It's shrouded around with that iron thing that focuses the field, and this happens to be the objective lens. But let's talk a little bit about lens terminology. So you're going to hear these words a lot if you do much electron microscopy. We talk about under focus, over focus, and in focus. So under focus means you turned up the, over focus means you turned up the current too much in the coil. It means you bent the rays harder than you thought they did, and you end up focusing above the plane. So if this is your sample here, this is just a carbon film. Over-focused would be this, and you can tell because you can tell by the color of the fringes at the edge. These are called Fresnel fringes, And because this is black and white, you know that this is the overfocus condition. So if you then turn the knob too far in the other direction, you end up not focusing them in the correct position, and this is called underfocus. And underfocus is here, right? And then when it's perfectly in plane, the contrast goes way down, and you see more features here. So that's underfocus, overfocus, and in focus. Okay, so now we're ready to talk about these first lenses. This is the condenser lens. This is the thing that's supposed to take the beam and put it on the sample. One more thing we need to know about are apertures. So aperture is nothing but a hole that limits the number of electrons or any particles that go through a lens, right? So if we put an aperture in here, we've limited the number and angle of electrons that can go through. In the condenser system, in most regular electron microscopes, we have two lenses, C1 and C2, and we mainly use an aperture on C2. And the whole point of this is to take that source that we made up here, focus it down into a crossover, and then refocus it onto the sample. And in a two-lens condenser system, the advantage of the reason we use an aperture on the C2 lens is to limit the range of angles that actually come down on our sample. And this means we get a more parallel beam that's more coherent. Now the Cryos actually has 3 condenser lenses, and that's a nice trick actually, because then you don't need to do this anymore. You can set the parallel illumination condition independent of the apertures. But that's really the main difference between the Cryos and the Polar. And for our purposes, either one of them can achieve a good enough beam to do what we want. Okay, one more piece of vocabulary, tilt and shift. So oftentimes you have a beam of electrons going through a lens. If it were perfect, it would be going straight through the optical axis, which is the symmetry axis of the lens, and down through the hole. But usually this never happens because there's mechanical misalignments. It's really difficult to take a big chunk of metal like this and align it perfectly mechanically with the next big chunk of metal underneath it. So we use tilts and shifts in order to align that optical beam as it goes through the sample, and then we use it again actually on the sample. And this is how you steer your beam around on the sample. But I just want you to understand the difference between tilt and shift. So shift means you're keeping the beam with the same angle with respect to the optical axis or with respect to your sample, but you're changing its position. And you do that by pushing on the beam in the crossover plane. And tilt is the opposite of that. We're keeping the beam in the exact same position, but we're changing its angle with respect to the position, right? So when you're adjusting shift and tilt, this is what you're doing. Okay, and I should mention just very briefly that beam tilt is a very important thing to adjust in the condenser system as you go to the sample, because you really want those nice plane waves like Shore showed the other day, coming through your specimen and interfering with each other in a clean way. All right, the objective lens. This is the business part of the microscope. I'm going to remind you of the phase contrast slide that Shore showed yesterday. So if we had the perfect lens and the perfect electron beam, it would come in as a plane wave like this, and it would interfere with the Coulomb potential of the atom, whatever atom is a ribosome atom or any other atom you want, and it will shift the phase of the wave along here. And then we use the objective lens to shift the phase of the unscattered wave. These two will interfere with each other and create a pattern that we can then measure with a detector, right? But all of this assumes that this objective lens is perfect. The trouble is, as I told you earlier, this objective lens is not perfect. It's not even close to perfect. And that's why we need to talk about this CTF business and where it comes from. Okay, CTF, contrast transfer function. That's just a fancy word for saying how bad the lens is. And in fact, this is one of the main reasons why we use high energy electrons that are much, much smaller in wavelength than we need by diffraction. It's because the lenses are so bad that this actually compensates for that. So what I'd like to do is at least give you a sense of where these curves come from, these wiggly curves that Tony showed and that you're going to spend a whole bunch of lectures figuring out how to compensate for later. But I want to give you a sense of where they actually come from. And they come from the lenses, the optics, right? A perfect optical system would not cause this. Okay, so this is the ugly equation on the slide. Don't worry. So I pulled this out of my thesis, but even I don't want to remember this equation. It's a pain in the neck. And so, basically physicists had to come up with a way to describe all the different ways in which lenses are bad because they're so bad. And so this is the equation to do this. It's the Taylor expansion of the phase. And anyway, but luckily there's a nice way to sort of visualize lens aberrations. It was come up with by a very interesting fellow, this Dutch physicist here called Zernike. And Zernike is really famous because he invented the phase plate for optical microscopy. And I don't know if you know about this, but this was actually caused a huge revolution in biology, because before he came up with this idea, you were basically left with stain. You had to, any cell that you wanted to image or any biological tissue, you had to use a stain, you had to kill it, and you had to fix it. And by introducing the phase plate, this allowed you to actually image living cells without destroying them, because it increased the contrast inside the liquid media enough that you could image structures. So he won the Nobel Prize for this in the 50s. But the other thing he did, besides inventing the phase plate, was come up with the mathematics to describe the aberration in lenses. And in fact, these little images here are functions, and you can use combinations of these functions to describe the aberrations in any two-dimensional lens system. And there's something called a Zernike transform, which is much like a Fourier transform, and you can take these functions and populate them up and describe all of the aberrations in any given lens, pretty much any system you want. And we can actually measure these. This is a measurement I did a while ago of the aberrations in a lens. But ultimately, our goal is to create a beam that has a nice uniform region of phase in the middle, and that's the bit that we want to actually image our sample with, because we want our sample to be shifting the phase of the wave, not our optics or some other thing. And so I'm not going to go through too many of these, but I am going to talk about a few aberrations. Now, we can correct aberrations in one of two ways. We can correct them with lenses in there to try and compensate for the badness of one lens with another lens, or we can do it afterwards in software. When we collect the image, we can correct for the aberration by moving or by calculation, basically. So this is astigmatism. So what do I mean by that? Astigmatism you're probably all familiar with. So if you have a nice sharp image and it goes out of focus on one axis, it looks like this. If it goes out of focus on the other axis, it looks like this. And so oftentimes we're left with a compromise of trying to make something, as good in one axis as the other, right? And this is used for eyeglasses and lots of other things. But this is a very important aberration in electron microscopes. And if you remember back to this image, this is an astigmatic image. You can see that the focus is different along this axis than this axis. And we really try and correct this as well as we can using the lenses, because we have good lenses to do this. And not only that, but we have live Fourier transforms now, so you don't have to do it just by staring at a carbon film in the dark. You can look at it at the Fourier transform. So this is a very astigmatic Fourier transform of a carbon film like this. And as you get it closer to stigmation, this thing gets rounder and rounder, and when it's in perfect stigmation, it should be perfectly round in the Fourier transform. Right? And that goes back to the way those phases are shifted with respect to the axis. So we also talk about stigmation in terms of electron beams. So if we want, ideally we have a nice round beam that will illuminate the sample uniformly. But if it's not round, oftentimes it's caused by stigmation. So one way to stigmate an electron beam is to change the focus of the beam with respect to the sample. And what you'll see is an ellipse on one side. You come through focus and it'll be a circle, and then it flips to an ellipse on the other side. This is exactly the same thing. You're looking at that stigmation going back and forth. So ideally, you use the stigmators to correct for this until you have a nice round beam going through the convergence point. This is another alignment that you'll do ad nauseum if you use electron microscopes a lot. Okay, I'm just going to briefly mention one more of these guys here because they're important. This one here is one we talk about a lot. It's spherical aberration, CS. And this is a parameter that you have to put in to rely on every time you do a calculation. And it's a good idea to sort of know where this comes from. So spherical aberration is actually very simple. What it means is that your lens, instead of having the same ability to bend rays all the way away from the axis, is actually stronger the further you go away. And the reason it's called spherical is because if you make a glass lens in the form of a sphere, that's exactly what happens. The rays that are far away from the optical axis get bent stronger than the rays in the center, and that causes distortion, and so you end up with a lower resolution image. And so, and you might think that this is a bad thing, and well, in some ways it is. You can actually buy lenses to correct for this in an an electron microscope. This is what they look like. The problem is these lenses are extremely expensive. They cost about £1 million a pop. And as it turns out, for our purposes, spherical aberration is not really a problem. And the reason it's not a problem is that we're very good at fitting these things in software afterwards. So you use something like CTF find to actually fit these curves, and that gives you the spherical aberration as well as the rest of the constants to a high enough accuracy that we can compensate for this. There's another little detail that I'll just mention in passing, but actually we take advantage of spherical aberration because of the difference between these two. This is the defocus, this is the spherical aberration. What I haven't told you is that spherical aberration is constant for a lens. It's a property just of the geometry of this thing and how it was built. So it doesn't change with the current to good approximation. Whereas defocused is exactly what we're trying to change with the current. And because of that, we can actually shift the phase of this relative to this and make a pseudo-phase plate, right? So this is actually what we're using to generate the contrast in these terms, is the difference between these two aberration coefficients. Anyway, enough aberrations. So we've used our objective lens. We made this beautiful image with it. Now what are we going to do with it? So we're coming down underneath the sample now. And the first thing we're going to talk about is the objective aperture. So what's an objective aperture? Remember that an aperture is just something that limits the angles of rays that go through a lens. So if and I should also mention that the objective aperture is in what we call the back focal plane of the objective lens. And the back focal plane has this special property that it actually acts like a Fourier transform. And so if you look at the back focal plane, you see a diffraction pattern, right? And that diffraction pattern is showing you all the spatial frequencies that were coming out of your image. And so if we put an aperture in there, we get rid of all of these high spatial frequencies. So if we go back to max, that's equivalent to taking the Fourier transform, putting a low-pass filter on it, and ending up with an image like this. So the advantage to an objective aperture is it does indeed boost the contrast on your sample, but it does so at the price of throwing away the high spatial frequencies. And I'll mention one other little warning is that this objective aperture can also induce distortions into the beam that we don't model very well in the corrections afterwards. So be very careful if you're going to use one of these, and particularly for high resolution work. Okay, objective aperture. So now we keep going further down into what we call the projector lens system, which is down here. So what do we got to do with the image now? Well, we have to magnify it. As it turns out, the focal length of this lens is actually fairly short. It's a few millimeters. So the magnification there is not very high. We're trying to look at atoms here, right? So the good news with electrons is that it's very easy to magnify them, right? You use a lens like this, which is called the intermediate lens, and another projector lens, to simply take the image that came out of the initial objective lens and spread it out so that it's magnified. And then you take that image and spread it out some more and then put it into your screen. And because the angle that goes into each of these lenses is so small, these lenses basically act perfectly. You don't need to worry about them very much. They do take a little bit of alignment, but in general, the objective lens is really the only one we need to worry about because that's the one that actually formed the image. These are just spreading it out. Okay, we'll take a brief aside for electron diffraction just because everybody seems to ask about it, so I'll give one slide on it. So it's very easy to do diffraction in an electron microscope. You just focus the beam on the sample, and if you have a crystal, you get patterns of spots coming out like this, just like in X-rays. We can use those projector lenses to magnify that diffraction pattern and come up with an effective camera length, which is just like a camera length in X-ray optics. This gives you the magnification of those spots on the screen. And I'll tell you, there is an advantage to diffraction in an electron microscope. Even with a T12, a humble 10-year-old microscope, you can see 2 angstrom spots, no problem, right? Like it's very easy to do, and it doesn't take a very sophisticated microscope to do it. But the bad news, of course, is that you still have, if you want to solve a structure with it, you still have the phase problem, and of course you need a crystal, and you need a small crystal and a very good crystal. And I guess probably half the people in this room have spent the better part of their youth trying to make crystals of things, so I don't need to tell you anymore why that's a disadvantage. Okay, so that's diffraction. What next? So we have this magnified, beautiful image coming out of the objective lens. Now how are we going to, what else can we do with it? There's one other thing I'll mention, because both the Polara and the Cryos have one of these. You can put it through a prism. We call these energy spectrometers, and they have lots of different names, but basically what they are is a magnetic prism. So if you think about that equation that I told you at the beginning, B cross B, you can see that there's a velocity term crossed with this magnetic field. So if you use a magnet to bend the electrons around a corner like this, some of them that have higher energies will move in different paths from the ones that have slower. So in here you can put a little aperture that clips off the ones that are not moving at the same speed as the primary beam. And the reason that's useful is we can use it to remove the inelastic electrons. Shores told you yesterday that the inelastic electrons basically cause damage but don't give us imaging capability. And so for thick specimen, like the kind you would use for tomography, this can be particularly useful, because if you just clip off right around the primary beam here and get rid of all of these inelastically scattered electrons, you do increase the contrast in your image. This is just a carbon film, and this is with and without the energy filter turned on. Okay, filtration. So we've now made the image. How do we actually detect it? So we're down here, and actually on the real microscopes it's further down on the down on the column. But there's basically 4 different ways. The first way is just look at it on the phosphorus screen with your eyes, right? This is probably the lowest resolution way you can go. But the traditional way we detect these things is with silver. So if you put an emulsion of silver halide on a piece of glass that we call a plate, or you put it in a gelatin, which is what we call film, the electrons will come through, break bonds in those halides, and so then when you go and develop it, you can reduce that to atomic silver. And that silver forms a negative where it's been struck, forms a piece of silver where it's been hit by an electron and doesn't where it hasn't, and so then you get an image. And this is a really good way to detect electrons, actually, and that's why it was so useful for so many years. Recently, people realized that you could actually do this digitally. And so what they did was the following. That you take a high-energy electron, like I mentioned, and you put it into some phosphor. In this case, it's a fancy phosphor. It's a scintillator called YAG, but most of them are made of phosphors. And you convert that electron into a shower of photons. And those photons go through a fiber array, which then gets connected to a CCD camera, like you might have in any digital camera. And then in that CCD camera, those photons create a population of electrons, which are then counted. So each pixel here can give you a signal, which is a number, basically related to how many electrons hit it. The problem with this is that each time you do one of these conversions, you lose a lot. You lose in different ways. You lose electrons because some of them come out. You lose photons because they're coming out in all directions. But you also lose statistically because the population here is a statistical ensemble related to the initial one, and then this is another statistical ensemble. And so in the end, you end up getting maybe 1 in 5 of your electrons being properly counted. And so this is a very, very inefficient way to collect these electrons. And because, as we said before, damage is limiting everything, you really want to count every single one of these electrons as best you can. So I think most of you have heard about the fact that there are now these interesting things called direct electron detectors, which are digital, that have largely been developed in this lab along with some other collaborators elsewhere. But Greg and Wazi and Richard have spent many years advocating for the fact that you really need every one of those electrons in biology because you're killing your sample with every one of them. So the better we can collect these, the better we can do structures. So the first generation of these direct electron detectors looks something like this. The pixels that actually do the business of making a signal are up here. So you have a high energy electron that comes in. It actually goes right through all the wiring and excites up some electron hole pairs, which can then be counted in this device. The trouble is that as this goes through and into the wafer substrate that's beneath it, these really high energy electrons can keep on scattering. And when they scatter, they can often come back out and trigger signal in a pixel that is not the original pixel where it came in the first place. Just some acronyms. This CMOS detector is what we talk about when we call this thing. That stands for complementary metal oxide semiconductor. This is just the type of processing that is used in the design of these particular types of computer chips, which is used throughout digital cameras these days. And that's as opposed to CCD, which is the previous one. Okay, so what can we do about these? So this is the real breakthrough recently, is to get rid of all of this material behind here. And this is what we mean by back-thinning. So you had some 500 micron or more silicon wafer that you made this chip on top of. If you get rid of a lot of that, then these backscatter events don't come back, and actually you end up with a much better signal, right? Because these guys are noise, whereas these guys are your real signal. So the less of these you have, the better off you are. And the new Falcon 2 detector, which we have now, is an order of magnitude difference in this thickness here. And that's really what was the breakthrough to increase our signal to noise and allow us to do these beautiful structures now, right? And so the next generation will be even smaller than that, and we'll do even better. Okay, this is what one actually looks like. Greg was kind enough to give me one of the prototypes, actually, which you can again come and see afterwards. It's a bit smaller. The real one is 6 centimeters on the side, so it's almost the size of this whole printed circuit board, but the actual chip is right here. So you can see what these things look like, and they really were developed here, and it's very exciting to be a part of this new technology. So this is the drawer basically that goes inside under the camera. So when you hear that when you're pushing the camera in and out, this is what you're doing. You're moving this into the beam line. And the bottom line is this. So a CCD, phosphor-coupled CCD, would probably be somewhere down here. And this is detective quantum efficiency. You can think of this as quantum efficiency. It's just the number of signal you get out based on the amount of electrons you put in. So the higher this curve is, the better. And we measure it in terms of spatial frequency because we need as much high-resolution information as we can. So the higher this curve is, the better, and the further it extends out to high frequencies, the better it is. So Greg has done a beautiful job of measuring this for the various detectors that are on the market right now, and we have both this one and this one. These are both on the Cryos. This is a competitor, another detector, which actually has very low noise electronics, which is you can see just based on how noisy these curves are. But unfortunately, their quantum efficiency is not as high. So you can see why we're beating film now, and it really is a big difference. So I mentioned one other detail. This lower resolution information here is probably quite useful for doing the alignment of particles, and so there may be some advantages to using this one, but in particular circumstances, but there may be other, mostly advantages to having the high frequency information here. But as these get better and better, which they will, these curves are going to go all the way up near 1, and Richard promises me that we're going to be up here soon, so that will be very exciting. Okay, some parting thoughts. What microscope to use? Well, I mentioned, the T12s are really sort of the entry point. You use those for screening. You can use them for diffraction. You can use them for checking all of your grids. But the Polara and the Cryos are really a different type of microscope entirely because they don't have these. They have real FEGs. But I do want to stress the point that the Polara, in every optical way, is pretty much as good as as the cryos. You do not need a cryos to do atomic resolution. I show this slide because this is the second, this is page 4 in my notebook when I joined the lab. So the first week I was here, I went on the Polara and put in a hunk of metal here. This happens to be aluminum, and easily got beyond 2 angstrom resolution in half an hour. And that's because we have an extremely well-maintained electron microscope facility here, and because these microscopes have never been limited by the optics. It's always been by the samples, our ability to collect the signals, and our ability to process the data. So the bottom line is, every time you come up to a microscope, or at least every time I come up to a microscope, I put in a test grid like this one. This is, for example, platinum iridium. And I check the alignments, I do whatever alignments I want, and I make sure that I can generate a pattern that looks like this. Right? And if you do that first, then you know for certain that the optics are not going to be limiting your experiment. It's going to be your sample or something about it. And if you can't generate one of these patterns with a test grid, then you should talk to somebody or get some help or figure out what's going wrong. And I think that's really important. Because if you can't generate a pattern like this with a hunk of metal, you'll never be able to generate a micrograph like this with the beautiful set of ribosomes or any other particle you want. And so I guess the take-home message is just make sure that the optics of this system are really not the thing that limits you. It's your sample, because it should be that. Okay, so I hope I've opened up the box a little bit for you. It's a mysterious what goes on inside of these things, actually, but it's not intractable, and I think you know who the real doctor is. I'll leave you with one quote from a physicist from many years ago. So Feynman said that, if we just make these electron microscopes 100 times better, the biology would become much easier. And he said this in 1959, and Tony gave a lot of the history of pushing it from 100 angstroms down. And 100 angstroms to an angstrom, and I would say we're getting close. So this is a pretty exciting time. And that's it.
Thank you very much, Chris. That was very clear. Does anybody have questions? We can do them now, because Chris will also be reminder.
What do you actually do physically to the lens to correct for astigmatism, or is it not the lens that you're changing?
This is the lens. You can correct for astigmatism by creating an asymmetric lens that bends the rays more on one axis than the other. So you create a magnetic lens that has multiple poles in it, and by doing that you can bend one axis more than the other.
So you're putting mechanical force on the lens to change its
No,
shape?
you're just changing the current. So it's an additional lens that applies another field to the device that goes on one axis versus another in order to compensate for it.
Do you see any improvement in the near future on the lenses that will give us something meaningful? I mean, better lenses are going to be in the market or not really?
Well, there are better lenses on the market now, but we've really not been limited by the quality of the lenses in biology till now. Right, so like I showed you that spherical aberration corrector. Those have been around for about 8 years now. They're very expensive, and there's the material science people down the street buy Titan, and they put 2 of them on there. But we really don't need to, because we're not limited by those aberrations yet. Now, it may be in the future, if we really push this resolution high, that we may have to start thinking about that, but right now we don't need it.
Any other questions? If not,
How about the faceplate in EM that has been discussed for a long time, people working on it?
Yes, so I didn't go into that at all, but so the idea behind a phase plate is, if you think about those polynomials, the way phase contrast works is you take your sine wave, and if you have a perfect phase plate, it shifts it by a quarter of a wave, and that turns the sine into a cosine. And so now the waves that got scattered by the material will constructively interfere with the waves that don't get scattered. And that's what generates the contrast. So we do a pseudo version of that by shifting the defocus relative to the spherical aberration. But ultimately, if we could make a perfect phase plate that would shift that all the time, that would be even better. The downside to this is that no one's been able to make these reliably. I think Nigel made one of these almost 40 years ago that worked, but it's making them robust and reliable so that you can take hundreds or thousands of images like we do now to make it interesting. There are some particular advantages to shifting that sine to a cosine for recovering the low frequency information, which is also very important for tomography. So the tomographers are very interested in this as well. So if you can make them, it would be great to have one, but we have to be sure that it works.
Perhaps next course we can discuss them in detail. Yeah. Okay, thank you very much, Chris.
Sure.